Ja, ik mocht er snel iets proberen zeggen.
Good morning, everyone.
Yeah, but since Dana is not here, we don't know if gonna check. Yeah.
I think here the audio settings on like that.
Anna was asking if she could follow the presentation online.
The Wi-Fi?
It's FSE, right?
Yeah, it's there. I used it this morning, so yeah, just hiding.
Oh, right.
Now you hear that?
But you can
I get it.
maybe just put the volume on. You can create a feedback loop that works.
I guess. Okay.
Yeah, okay. We can create feedback loops, so.
But I see it.
We have a few of these.
Good morning to everyone. Before we start, a reminder on behalf of the RAM session chairs, if you want to give a RAM session talk, please upload your slides until 10. Yeah. Register until 10, and then you can be able to update them until 1. Okay. But the 10-hour deadline is important. So welcome to the first invitation talk of this FSE 2024. We're very happy to have with us Maria Eichlseder. So Maria is assistant professor at the Graz University of Technology, and she obtained her PhD in 2018. So Maria is a specialist in design. She's particularly among the designers of Ascon, the winner of the recent NIST Lightweight competition. And she's also an expert in cryptanalysis. So she has worked in the cryptanalysis on many hash functions, authenticator schemes, and their underlying primitives. And in her work in cryptanalysis, she has put particular accents in automatization. She has developed a lot of this branch about automatic tools. And this is something she's going to talk to us today. So let's welcome Maria.
Thanks a lot for the introduction. So yes, indeed, I want to talk a bit about tools for cryptanalytic attacks and how they can help the designer or the cryptanalyst to improve their work. So to get there, I first want to give a brief motivation, and then I want to first dive into a more introductory part where I want to show some of the basic methods that are now very widely used in many, many papers. So in particular, I want to focus on the search for distinguishers with mixed integer linear programming or SAT solvers, just to give a basic introduction to what we're talking about. I will talk a little bit about the advantages and disadvantages of these algorithms, and then I will try to argue why, despite these very useful tools, there is also a lot of reason to develop dedicated tools. So not to rely on off-the-shelf solvers, but to do something on your own, and how it can improve the process. And near the end, I want to have a sort of a higher level view about the whole cipher, because when we talk about attacks, of course, we don't only need a distinguisher. We also want to do something with it. So in this last part, I want to talk a bit about how tools can help find optimized key recovery attacks, and finally share a bit or a few thoughts about frameworks and the role that they can play for the community. So for the motivation, of course, this is a very broad area. I want to focus on a particular kind of cryptanalytic techniques in this talk. So mostly I'm going to talk about distinguisher-based classical block cipher cryptanalysis. So the one classical example being differential attacks, where we are considering a block cipher and we're trying to make some predictions. If I look at a pair of inputs with a particular input difference delta x, what can I say when I go through the algorithm? So usually I make some sort of predictions with a characteristic where I'm describing a potential path of what could happen at each step, in order to, at the end, make some prediction about the potential output differences. For example, one particularly likely output difference. So once I have found such a distinguisher, I can do a lot of things with it, which is why many people, including tool developers, often only focus on this part. Because if you know how to find good characteristics, you can either use it as a starting point for attacks, or as a designer, you can use it as arguments why your design resists these attacks. So once I have a distinguisher, the job is, however, not over. So I need to do something useful with it. In case of differential cryptanalysis, there are many different things I can do. So I can either try to use this distinguisher quite directly, just to distinguish the block cipher, or, for example, If I can cancel the difference in a way, I could use it, for example, to create collisions, or I can predict the difference to create a forgery or something like that. But much more often what people do is they attach a few rounds and then do a key recovery attack based on this distinguisher. Now in my pictures, I usually only have the key recovery part at the bottom, but of course it can also be at the top as well. Now this basic pattern, which most of you are very familiar with, of course also applies to numerous other attacks. For example, in linear cryptanalysis, where I'm talking about linear masks instead of differences. And I can similarly use this distinguisher in a quite straightforward way. For example, to learn a tiny bit of information about some data at the beginning or at the end of the cipher, or I can again do a key recovery attack. And while the picture here looks very simple, the specific key recovery techniques are quite a bit different between these different designs. What they usually have in common is that I somehow need to determine which parts of the key I need to guess in order to recover part of the state here and evaluate my distinguisher. But the specific ways to get there are quite different between attacks. So another attack family that I want to keep in mind are integral attacks. Now, these are not quite as obviously characteristic based, but they can be. So an integral attack is an attack where I'm not considering just one input or a pair of inputs, but a structured input space of messages. And I can make some prediction about the output of the cipher when summed over all of these elements in the space. So one big difference to the previous slides is that this is not a statistical or probabilistic property, but there are still things like monomial trails or division trails where I can also make a prediction through the cipher or follow a characteristic through the cipher. And again, I can do similar things with it as in the linear case. So in all of these cases, the major part of the attack is to find a good distinguishing property. So this is the hard task that we are dealing with. And over the years, we've developed quite a few ways how to do this. The most natural, of course, being to try to do this by hand. Now, this does actually work for some designs. For example, if it's particularly structured, like the AES, for example, where these kind of characteristics have already been taken into account in the design, which also makes the job easier if we try to find characteristics or deduce bounds. But very often, for many designs, this is by far not feasible. And for this reason, there have already been for a long time efforts to use the computer to guide and aid cryptanalysis. And originally, this was mostly with the help of dedicated solvers or algorithms. One very famous example being Matsui's branch and bound algorithm, where you try to enumerate or go through the search space of potential characteristics, but you cut off branches that don't look promising. So dedicated solvers are great because you can put a lot of cryptanalytic knowledge into the process. You can use a lot of guidance for the solver. The downside, of course, is that now instead of being a cryptanalyst, you also have to be a very efficient programmer. You need to write efficient code, which not all of us are perfectly great at. And it also costs a lot of time if you want to do it for more targets, for example, for diverse targets. So this is one of the reasons why using general purpose off-the-shelf solvers has become very, very popular. So these are solvers which are programmed by non-cryptographers for very general tasks. So they usually process some sort of input language that describes what kind of solution we are looking for. And then you have a ready-made, a very efficiently written solver that does the task for you. So this includes things like SAT solvers or their generalization, SMT solvers, but also mixed integer linear programming or constraint programming, which is a sort of very general term that means different things to different people. So here you have now a general language that you need to express your cryptanalytic task in. And if you've done so, the actual work is not done by your code, but by somebody else's code. So let's first have a look at this last method. So at finding distinguishers with these off-the-shelf solvers. So the basic process between these different tools is usually very similar. You have a language in which you can express constraints. These constraints should describe what exactly you're looking for. So you're describing, for example, what a valid characteristic looks like. Now, you can already make decisions at this point for how precise your model is. So for example, you can look just for an activity pattern of active S boxes. So look, for example, at a word-based pattern. You can already use this to deduce bounds or things like that. If you want to do an actual attack, you usually want something more specific. You want a more precise solution. You want an actual bitwise differential characteristic. And of course, the more precise you want things to be, the more effort it is typically for the solver. So there are some trade-offs to make here. In addition to modeling what you're looking for, you should also express what it means for a solution to be good. So you deduce some sort of cost function. If you're looking for an optimal solution, if you're just looking for any solution, then you can skip this part. And finally, you have to think about what you want to do under these constraints. So do you want to have one optimal solution, one good solution, which is not necessarily optimal? Do you want to prove that no solution exists? So there are, again, different things you can do. But to make it a bit more concrete and to give you a sort of mental model, I want to have a look at a very simple example for how to do things with mixed integer linear programs. So this is based on a very well-established branch in mathematics on linear programming, which is a kind of optimization problem. And as the name tells, it's by nature a linear program, which means you have some decision variables, which are real numbers or real vectors. And then you express, on the one hand, an objective function that you want to maximize or minimize, which is linear. And you have some constraints that your solutions should satisfy, also linear constraints, which can be also, all of these are essentially defined by these weights that you give to the decision variables x in either the objective function or in the constraints. And then you have a problem like this. So you want to maximize or minimize overall values of these decision variables, your objective function under these constraints, and usually some non-zero, so positivity constraints. Now, if you look at this, it doesn't look very attractive for cryptanalysis, right? It speaks about real numbers. It can only do linear things. So by itself, it's usually not that much use. But there is a generalization that is a lot of use, and that is mixed integer linear programming, which is the same thing as above, but we are now constraining some of the variables to be integers. So some of our variables can still be real numbers, but some of them we can constrain to be integers. And this suddenly makes the problem a lot more interesting and also a lot more complex, because we've now turned it into a partially combinatorial problem. So to understand why this is actually more difficult to solve for the solver, let's have a quick look at what an LP problem actually looks like. So you're having some decision variables. In this example here, we have two decision variables, x and y, and you have some constraints. So each constraint divides the space you're looking at into two half spaces, and one of the two half spaces is the good half space. And within this half space, you're looking for an optimal solution. And the nice thing is that you can show that these solutions, they always sit in corners of this convex set that you're looking at. And this means we can have very efficient algorithms like Danzig's algorithm to find these solutions. But if we now turn this into a mixed integer linear program, we're now only interested in these vertices here. And even though in this example we don't have a lot of them, generally there are a lot, and we can't as easily characterize the optimal solutions anymore. So this is why MILP solvers essentially mix the basic linear programming algorithms with some branch and bound techniques, which are actually quite similar to Matsui's algorithm. Okay, so with this model here, with this integer-based model, how can we describe a design? So I want to give here a very classical model that has been proposed by Muha et al. Already many years ago. And the goal is to find truncated characteristics or activity patterns for the AES. Of course, this is a task we actually do know how to do by hand, but let's use it as a simple example. So for the decision variables here, what do we want to solve it to decide? We wanted to decide which of these cells of the AES are active. So we want to describe the characteristic, which means these should be our decision variables. So every cell here should be one decision variable. It can be either 0 if the cell is inactive or 1 if it's active. Now we can very easily describe the individual steps here. So what happens during add round key? Well, it doesn't influence the activity. Sub bytes also doesn't influence the activity pattern. However, of course, the cells which are active at this step are very interesting for us because they determine the cost function we're interested in. We want to minimize the number of active S boxes. For the next steps, well, shift rows is just a variable renaming, but essentially the values themselves remain unchanged. So the most interesting step in this sense is the mixed column step. So which transitions over mixed columns are active? In case of AES, that's very easy to say. It's all transitions that satisfy the branch number of the function, which means if there is at least one active cell in a column in the input and output, then there must actually be at least 5 active cells in the input and output. So this is how we can describe things. Let's now put this into a formally specified model. We can see because most of these steps essentially don't change anything, we don't really need to store variables for each of these steps, but only for the steps where something interesting happens. So we're going to essentially have just one variable, one binary variable for each active in each, for each cell in each round row and column. And we're going to use some helper variables, which is a very frequent pattern in MILP problems, which tells us whether a particular round is, so whether mixed columns is active in a particular round. So in the previous picture, for example, this helper variable would be 1 in this first column here, and it would be 0 in the other columns here. The actual problem that now describes our characteristics is actually super short. So we want to minimize the sum over our active S boxes. And our conditions are only 2. So for each index at least. So the one is the branch number. So we here in the middle, we see the sum of all related variables at the input and output. And we want to have that their sum is at least the branch number. But we only want to put this constraint if the row is actually, if the column is actually active. So this value here is 5 if the row is active and 0 if it's not active. In order to make sure that this activity variable actually takes the right value, we can put another right-hand side for this inequality, which essentially ensures that. And finally, of course, we don't want to find trivial characteristics, so we can put some non-triviality constraint. So this is nice and short, and it's also very convenient because you can write it down in a simple mathematical description, which means you can very easily include it in your papers in a sort of technology agnostic way. But if you do want to have something technology specific, if you actually want to implement it, there are tons of different solvers and interfaces that give you some language to describe these constraints. So here's an example done in Sage, which has a very natural language where you can just express the constraints in a very straightforward way. Okay, so doing simple things with MILP is very simple. But of course, in more interesting applications or in more diverse applications where we're looking for more complicated characteristics, we might need a bit more ingredients. And in particular, we need more complex models of what constitutes an allowed transition in my characteristic. So this pops up, for example, if I'm staying in the area of activity patterns, then it shows up, for example, when I'm modeling different matrices which are not MDS, for example. So there I need to think a bit more. It also pops up if I try to do a bitwise model where I want to model the possible transitions through the DDT or LAT. And this task has a specific name. So what I'm trying to do is I want to translate a vertex representation into a half space representation. What this means is I'm given some sort of table of possible transitions. So for example, if I'm looking at activity patterns going through XORs, you can think of it like DDT with 4 rows and 2 columns. Then I can either describe it in table form, so like a truth table, or I can turn this into inequalities. So because each inequality defines a half space, this is called the half space representation. And there are actually some generic approaches how to do this. But of course, the bigger the table, the messier your equations become. So this, after some size, for example, if we are speaking about DDTs for 8-bit S boxes, this becomes very complex. So different authors have described approaches how to do this. So here's, for example, a nice systematization of knowledge paper on this topic, but it very quickly becomes infeasible to actually run this. And additionally, it also becomes a relatively unnatural description from a cryptographer's view. So for this reason, there have been a few other approaches, other languages which have been used. One very natural choice is satisfiability solvers, where you're not describing linear equations, but instead conjunctive normal forms. So a conjunction of a disjunction of literals, which are either variables or negated variables. And there are tons of very efficient solvers and a very active research community in this area, which makes them quite attractive. And in particular, there is also a lot of progress over the years. Unfortunately, this is also a somewhat clumsy description language. So if you want to describe something like this in your paper, it can also be quite messy. But there are some higher level abstractions that can be very useful here. For example, satisfiability modulo theories, which accept a more general grammar. For example, bit vector additions, integer additions, and things like that. A very popular tool in this area or solver is STP, the simple theorem prover, but there are a couple of others. And finally, more recently, there have been even more general solver languages or families which mix some of the aspects of satisfiability with some of the aspects of, for example, mixed integer linear programming, where you can also optimize. Because one big difference between these here and MILP is that a SAT solver or SMT solver only solves for satisfiability, so they can't optimize anything, which is a bit inconvenient if we try to do cryptanalysis. Okay, so there are some downsides and upsides to each of these. If you do want, for example, to use a SAT solver to optimize something, like to find an optimal characteristic, you need to do a sort of workaround, because you can only ask satisfiability questions. So what you could do, for example, you could run the program many times. You first ask, is there a solution better than X active S boxes? If no, then you can ask for X plus 1 or X minus 1, depending on what task exactly you are trying to do. So this is a bit inconvenient, but still feasible. The nice thing about these SAT and MILP solvers is that they're more natural language to describe Boolean constraints, which we, of course, have a lot in cryptography. Another advantage is that they're not only useful for finding characteristics, as we've discussed so far, but you can also turn other crypto problems into SAT problems. And this has actually been done much earlier than characteristic search. So for example, you can turn a pre-image problem or a key recovery problem in a relatively straightforward way into a SAT problem. And this has already been done in the early 2000s, for example. But the focus here is more on the distinguisher-based ones. A downside of the SAT solvers is that they can't optimize, and it's very difficult to actually express a cost of something, so a sum of costs, because implementing these summing building blocks can turn very heavy, unfortunately. Another downside is that the algorithm is inherently quite serial. And of course, we usually want to parallelize our tasks if we have a good server or so available. So for this, you also need to find a workaround. There are different approaches, like, for example, some SAT solvers try to automatically partition the search space in some clever way, and then run each of these subtasks on a separate thread. But unfortunately, in my experience in cryptographic problems, this doesn't work very well, because very often one instance is the hard one and all the other ones are super easy. At least this is the case for most of the partitionings that these solvers find. Okay. A general disadvantage of all of what I've said so far is that you only have a very limited influence as a cryptanalyst on the search process. So you can only give relatively limited guidance about what you expect to be good strategies, good search strategies. And this is one of the reasons why dedicated algorithms have also become quite popular. And one particular area where we've seen a lot of dedicated algorithms is the area of hash function cryptanalysis. And I think there are a lot of good reasons for that. One reason is that hash functions very often have a large state. And the larger the state, the more difficult it may become to solve things in a generic way without additional guidance. Another difficulty is that for hash functions, we usually don't just want to find characteristics. We want to find collisions, for example, or other more advanced tasks. And these are typically the result of a multi-step process. And modeling a multi-step process in a solver is quite challenging. So a few examples which have been very successful in different hash standards include, for example, the Hashclash project, which is so advanced and usable that you can create your collisions with custom constraints with, for example, a few days ago, there have been examples which are only based on ASCII characters or things like that. So this is both due to the vulnerabilities of SHA itself, but also due to the immense effort that has been put into this project. Another tool that I want to talk a bit about is the NLD tool, which has been developed by Florian Mendel, Martin Schleffer, and others from IAIK, and has been used quite successfully to find collisions and semi-freeze-start collisions for reduced SHA-2. And finally, for SHA-3, there is the Ketchak Tools project, which also has some very efficient and clever dedicated search algorithms for characteristics, which perform quite a bit better than the generic or the off-the-shelf solutions. So let's have a quick look at this SHA-2 application. The basic internal process of this tool is quite similar to what SAT solvers also do. So SAT solvers generally follow a guess and determine search strategy. This means that they start with all decision variables undecided. They pick some variables, make an assignment, and try to continue from this assignment. So if there is a contradiction, they try to detect it and undo their guess. But if it works, then they continue guessing. And while SAT solver do this on a very small scope using only CNF formulas and some very, very simple detection mechanisms for contradictions, we can actually apply this to more general building blocks. For example, to parts of hash functions or to small differential circuits. And this is also what this tool does. And the goal is not only to find characteristics, but also solutions for these characteristics. For example, for hash collisions. And there have been quite a few papers which are now about 10 years old for SHA-2. Now, I want to mention here that very recently there have also been efforts at achieving similar results or even better results with off-the-shelf solvers. But this has required quite a bit of effort to get to work, showing also the advantages of the dedicated approach. Okay, so the general process, I've already hinted it. It works by finding a particular notion of what a decision variable, what it means for it to be determined or undetermined. And this notion can actually change across the algorithm. So in the beginning, undetermined, for example, could mean I know nothing at all. And determining it could mean I set the difference to either 0 or 1. Whereas later in the search, undetermined might mean I do know the difference, but I don't know, for example, if there is a difference, is the pair of bits 0, 1, or is it 1, 0? So you can model different stages of the attack with this. And at each stage, you pick one of these values which are, according to your current definition, undetermined. You determine it, and then you see what happens, what you can deduce from this. So for example, you can make differential deduction. And if this works, you continue. If you find an error, then one of your previous guesses must have been wrong. So you undo one of them and continue with the alternative choice in the search tree. What this then looks like is, in the example of SHA-512, where we have essentially one large block cipher and its key schedule, which in the hash case is its message schedule. And we are looking for inputs, so a chaining value and a message, which produces, for example, a colliding output. And to actually find such a collision, I can now use some cryptanalytic understanding to structure the search process. So for example, in the case of SHA-2, the strategy is typically to first identify a potential local collision, so a pattern of active message words and the corresponding cancellations. And then in several steps, you determine the specifics. For example, you know there are some parts which should have a very high probability, so few differences. So you try to fix this part first. And then later, or you try to fix the characteristics for these parts first in a good way. And then you try to find actual solutions by solving the heavier parts and hoping that they work out for the higher probability parts. So this is an example of such a multi-step process, which, as I said, is very difficult to model in a SAT solver. So here we can use this knowledge that it helps a lot to first guess or fix, for example, a pattern here before we continue with the rest. In a SAT solver, this is very hard to communicate. Okay. Another area where we do have these multi-step processes and where we'd like to find a model for them is key recovery attacks. So I want to share a few thoughts and examples of how this can work. I have to say that a lot less has been done in this area compared to distinguishers, and there are quite a few reasons why this is the case. One pragmatic reason is that there tends to be fewer choices that an attacker can make in the key recovery part compared to the characteristic part, which means doing it by hand can be more feasible than finding characteristics. So this is a reason why it may seem less necessary. However, if you look closer, if you look at the really good attacks, you see this really doesn't actually apply. So there have been a lot of different optimization techniques for the key recovery parts that involve a lot of choices and trade-offs to make, making it quite impractical to do things by hand. Doing it by hand is also a very tedious and error-prone process, as we see repeatedly with small errors in different key recovery strategies. And there's also a final other very important reason, and this reason is that the best distinguishers do not necessarily lead to the best attacks. So if I have a two-step process where I first find an optimal distinguisher and then do the key recovery by hand, for example, then it might be that I'm missing better attacks which use a distinguisher which looks a bit worse, but is a lot better compatible with key recovery strategies. So this last reason in particular is a very good reason to use tools. So I'm showing here now a few examples of how tools have been used in the past. This is a bit of a biased selection. So I'm certainly not claiming to cover all of it, but I want to show how diverse key recovery strategies and their models can actually be, and which different questions you can ask a solver in key recovery. So as a first and simple example, this is a tool which doesn't work in a distinguisher-based model, but which directly does guess and determine attacks on designs. So you want to know which keys do you have to guess in order to determine a certain part of the state or determine whether the key is consistent. So in the example here, you see the application to 3-round AES of this tool by Hadipur. Now, by itself, it doesn't fit the pattern of attacks that I'm talking about, but it's a very useful building block that we can also see used in other attacks. So having this sort of step-by-step strategy where you try to, in a clever order, guess some key bits to determine other parts, this is something that also shows up in linear or differential key recovery. So for differential key recovery, there is also a tool that has been developed in my group by Nagela. And this is specifically focused on finding optimal differential attack strategies in a setting where you have, so in an SPN-based setting where you have some differential characteristics or a cluster of characteristics. And you want to deduce an optimal guessing strategy under different constraints, like, for example, restrictions on the memory, different choices that you can make in the distinguisher, like, for example, what we typically do in a differential key recovery is when you have a distinguisher, which would be the connection here at the bottom, we typically propagate this outward with probability 1 and then build the key recovery on that. But you can also make choices in between, where in some cases you choose to ignore some cases in order to improve the overall complexity. So this tool uses internally a MILP solver in order to find the best configuration in this setting. Another tool that has appeared very recently is the QRD tool, don't know how to pronounce it exactly, by Boura et al., which uses a very different approach to also find optimal key recovery attacks according to a certain definition or a certain strategy. There are also a few examples from integral cryptanalysis that I want to mention here. So one example is this graph-based building block that we've used in some attacks on warp, where we want to take advantage of some of the optimization techniques that we can do in integral cryptanalysis. In particular, one very powerful method is the FFT approach, where you're using, where you can significantly speed up the attack and get rid of this product of the data complexity and the key guessing complexity, essentially. The thing is, in order to apply this approach, you ideally want this key recovery part, where you're trying to recover one intermediate cell, which depends on many ciphertext and key values. Ideally, you would like this function to be in the shape of f of x plus c. So ideally, you want just a whitening key at the output, and then a function applied to this XOR of the ciphertext and key. However, usually when you do a multi-round key recovery, of course, you don't have this strategy. And what we try to do here is we try to take such a graph-based, so a directed acyclic graph-based representation of a few rounds, in this case of a Feistel construction, and try to restructure this graph in order to maximize the part of the key that is used in this whitening structured way and minimize the number of internal key cells that we need to treat differently. Another example is the autopsy building block. So this is also just a small script which also works with a given distinguisher and then tries to automate the partial sum strategy for this particular pattern. So in partial sum technique, we evaluate the sum of our samples at a particular intermediate value by doing a step-by-step guessing approach where we guess some key cells, reduce the intermediate sums in a compressed representation, and then continue. And the ordering in which we do this has quite an influence on the total complexity. Okay, so what all of these tools here have in common, or these tool is maybe a bit generous for some of them, but what all these scripts or tools do is they work with existing distinguishers. So they only try to optimize the key recovery part. Now this can help improve quite a lot of results. So all of these tools have been applied to find new and improved results, but they cannot directly be combined with distinguisher models because they're separate things essentially. So what we would ideally like to have is a combined model of both the key recovery part and the distinguisher part. And one big restriction for this is that it only works if we have satisfiability-based distinguishers. I'll explain in a moment what I mean by that. Another reason what makes this quite difficult is that the complexity formulas for key recovery attacks can be quite complex in themselves. What I mean by this is they are very often composed of a sum of terms. Very often you have a mix of polynomial and exponential terms, and expressing this in a language like MILP is very messy compared to, for example, distinguishers where you can simply add the weights. So you have a very simple linear representation of the cost. Here, this is not necessarily the case. An additional difficulty is that even where we do have complexity formulas, they very often make some simplified assumptions about what happens at each step or how many values survive each step and so on. So if you deduce an attack under these simplified assumptions, it is not necessarily correct. So you usually still like to double check it manually. We also often have this multi-step process. So if we want to represent this in an MILP model or so, for example, a step-by-step key guessing, then we essentially need something like a separate set of variables for the key guessing progress at each step, or another similar representation of this multi-step thing, leading to very heavy models. Even if you've solved all of this and you have a model, you need to take into account that different designs have very different key schedules. So the key schedules, in my opinion, vary a lot more between designs than the round function does. And this also means it's quite different what you can optimize for when you take the key schedule into account, if you do things like key bridging, for example. So if you have something, it's probably only going to work or be efficient for a very specific kind of tools. And finally, of course, cryptanalysts have developed a lot of different optimizations and strategies for the different types of key recovery, which means you need a lot of knowledge and a lot of time if you want to take all of these into account, for example, when doing integral key recovery or so. Or you need to just decide and go with one particular strategy which limits the applicability of your tool. So I think all of these are reasons why so far there haven't been too many attempts or efforts at doing an automated search for complete attacks. But there have been a few examples, and I want to show one of them. And one difficulty when we try to do this is that, as I mentioned, we want so-called satisfiability-based results. And this is particularly difficult for distinguishers whose validity we prove by proving non-existence of something. So this is a pattern that shows up in different attacks. For example, in impossible differential attacks, where we want to find impossible differentials where there is no characteristic, for example, between the input and output difference. Or it's the same case if we are looking for zero correlation approximations, or for different types of integral distinguishers, for example, based on monomial trails. In all of these cases, we would typically like to prove the non-existence of a connection. Now, this makes it very difficult to use in a combined model, because in a combined model, we would ideally like that the final solution that is returned by the solver describes one attack. But this means that one solution needs to represent one distinguisher and the key recovery for it, which is difficult if we are basing things on the non-existence of characteristics. So this means I either need to redescribe this not as the non-existence of something, but as the existence of something, or I need to use a quantified language, like, for example, quantified SAT, where I can use quantifiers like the exists or the for all quantifier. So instead of doing this, something based on unsatisfiability, where I first need to specify what distinguisher I want to check, and then I check whether it is a valid distinguisher, meaning no connection exists. I can turn it into a satisfiability-based approach, where I'm trying to describe all reachable differences, for example, from a particular starting point and from another one. And then I'm looking for a solution which consists of a proof of incompatibility between these two. Now, in this kind of description, I can now ask the solver, please find me an input and output characteristic which does have such a proof of contradiction in the middle. So this is essentially a miss in the middle approach, or an implementation of this approach, and it can typically be very efficient for the solver to run. It's usually actually faster than this one here. But of course, it is somewhat less precise, because I'm sort of approximating the set of reachable differences. I need some abstraction how I describe this, for example, as a truncated characteristic or so. And this means that I might miss some distinguishers in this way. But if I want to combine it for an attack, then this is the approach that I need. And this was applied, for example, in a paper by Hadipour et al., of which you will hear later today a talk on a follow-up work where you will hear more details about this. And in this paper, we worked on different kinds of impossibility-based attacks. So impossible differential attacks, where we find distinguishers described like this. So specifying a pattern of input and output difference, and then describing an incompatibility in the middle when I propagate. And together with this, the model also models the key recovery approach, which in case of impossible differential attacks means I need decision variables to determine which cells, which key cells and state cells are involved in the attack, so are necessary to reconstruct the value here. In which cases do I need the difference or the value of such cells? And when I have this, then I can deduce the filter properties and so on and deduce the actual attack. And something similar can be done for zero correlation attacks. So again, I need to model the involved cells and then have some estimate of how this translates to a cost function. Or we also did it for integral attacks. So I've put an asterisk here because in this paper, we only had a simplified representation or a simplified estimate of the cost of the key recovery. And later today, you will hear how to do it in a much more precise and efficient way. Okay, so finally, a few words about frameworks. Because this is ideally what we would like to have as a community, what would save us a lot of time. To not have to redo all of this work that I've described so far every time we do some analysis, but to have some reusable parts. And the question is, do we have such frameworks? So if you look at paper titles from the past years, you would expect we have a lot of frameworks because there are tons of papers which are called a new framework for, a new tool for. Now, unfortunately, I think many of these don't really satisfy the criteria that I would apply to a framework. So for me, a framework means I need to have a certain generality and applicability of the tool. So ideally, it works at least for one family of designs, such as SPN designs. It's even nicer, of course, if it works for more. And ideally, this framework not only consists in describing a theoretical framework, but a practical framework that allows me to instantiate a number of different designs. Ideally, I would also like to have some reusability and extensibility of the tool. So this means there should be some building block which I can reuse for every new cipher that I model, for example. Now, in many current frameworks or tools, what we actually see is that the framework consists of a large set of code files, and each code file describes exactly the SAT or MILP model for exactly one configuration of exactly one algorithm. And this is essentially copied with minor variations to tons of different other applications. So there is zero reusability, even though the individual files might be well readable. Another issue is the maintainability and verifiability of the tool. This is also hampered if I have this, this approach where I have a lot of duplicate code essentially, because I cannot verify or check easily the correctness of all of these copies of the code. So there is a lot of potential for errors. So ideally, you would like to have a smaller reusable code base which describes the core parts of your model, and then an easy way how to add new ciphers in this framework or context. Despite this, there are actually a few things that I would call frameworks. I've listed a few here. Again, no claim for completeness, but I think these are some very nice and useful contributions. So for example, there is the crypto SMT tool, which mainly focuses on finding linear and differential characteristics and also clusters, so estimating the differential effect for a lot of different ciphers. So many of them have been implemented, and the underlying technology is a general SMT or SAT encoding. So this is something very useful. Another very useful example is the Cascala framework. This is a bit more recent. And in addition to the above, it also allows to find impossible differentials, zero correlation, and so on. And finally, the most general framework on this slide, I would say, is GLASP, which does all of the above and also has a number of different distinguishers or tests that it can do, such as, for example, neural tests. And it's also a bit more general because it supports many different solvers. So it translates a particular problem either into SAT or MILP or CP or and so on. So it's a very general thing and also very recent or still in development. And I think there are also a few people you can discuss this with here at the conference, and they also have a booth outside, so they might be happy to talk to you. But still, most of these are primarily focused on the distinguisher part. So for example, the key recovery is not really taken into account. And it's also mostly focused on block cipher-based analysis. So for example, for hash functions, you would need more building blocks to really find competitive results. And of course, there are quite a few challenges if you try to design such a framework. So both for the person who is doing the framework or the team, and also for the people using it. And one of the crucial decisions to make is, how do you represent the ciphers on the one hand and the attack techniques or models on the other hand? What kind of interface do you offer? And the frameworks I've shown before, they take very different approaches for this. So some of them are more based on a more natural software or hardware, so circuit-based description. Some of them give an abstraction with some building blocks for a particular type of designs, like classical SPNs, and so on. So this determines a lot how usable the tool is. And then, of course, there are different trade-offs, like you can go for more efficient models or for more precise models. For simpler approaches, for more dedicated ones, which are then heavier to solve, and so on. So many trade-offs to make. But there is also one very big meta challenge with frameworks, I would say. And this meta challenge is incentives. So on the one hand, such a framework would have very high value to the community. But on the other hand, the way our academic incentives work, there is not really that much motivation to develop a very good and very usable framework, because this is a lot of effort, but not all of this effort is really publishable. And this holds on the one hand for the person who does the framework, but it also holds for the people using the framework, because it's a lot more easy to get a paper if you develop your own new framework or tool for something than if you extend some existing tool. So I think this is something we really need to rethink a bit when we are in committees, or also when we decide to write our papers. Do we really want to redo everything from scratch, or do we want to work a bit more collaboratively and reuse things other people have done? Not only the theoretical part, but ideally also the code. All right, so to summarize, tools and solvers are really a crucial ingredient for a cryptanalyst as well as for a designer. It's currently a very, very active area, and there are many open challenges. Some of them, like in every area, you want higher efficiency, you want higher precision, and so on. This also applies to tools. You also want a broader applicability. So far, there's quite a focus on SPN-based designs and some ARX approaches, but also most of the tools work on these distinguisher-based approaches. And there are many other attack techniques which don't really follow this pattern and which haven't received as much attention, I would say. Finally, as I've argued, modeling full attacks is really one area where I think there is a lot of room for improvement and a lot of work still to do. And the other big construction side, I think, is having reusable and powerful frameworks. And with that, thanks a lot, and I'm happy if you have questions for me.
Thanks a lot, Maria. So are there any questions?
I don't want to, maybe my voice propagates anyway. Okay, regarding the use of key recovery, we do have some preliminary results with MILP on optimizing also the key recovery for differential and truncating differential cryptanalysis. But there is one problem: it's very ad hoc. It can vary a lot cipher from cipher, so it's not generic. So there is something there, and I agree with you that we need maybe to pool and have an initiative to try to have everything modular and put together for everybody to use. Maybe there will be a paper with 1,000 authors, but why not?
Yes, indeed.
Sometimes when to do a discovery in physics, they have those, so why not in crypto?
Yeah, I don't really have too much to add to that, so I agree.
So, hi, thank you for the talk. So I have basically two questions. First of all, whenever we see automatic tools paper, we see that people try to optimize the number of constraint. Like people use heuristic tool like Logic Friday and Espresso or Christian as a tool, Super Bowl technique. Why this is important? I mean, does this help the solver? If we
So what you're referring to is, for example, when I'm doing an S-box model,
Yeah,
also
exactly,
that when I'm
exactly.
doing this H representation, for
when-
example, that I minimize the number of constraints. And in Boolean models, I can do something similar. I can try to optimize the size of the problem description. Now, this, I would say it does have some correlation with the actual complexity of the solver, but not always. So it's often the case that adding more constraints actually makes the solver faster because it provides additional guidance and allows it to exclude some solutions earlier. So there is no clear causality between the size of the model and the efficiency of the performer. The problem is we don't really have any good other placeholder metrics that we can easily measure directly from the model that tells us how efficient the solver is. I mean, there are some criteria that it makes sense to optimize. For example, in MILP, having more variables is usually a bad idea. So if you can get rid of any helper variables, this is usually a good thing to do. So but otherwise there are very few placeholder metrics that we can use besides the number of constraints. I think this is why there is some focus on it. But yeah, minimizing that definitely doesn't guarantee that I minimize the complexity. So understanding the complexity or predicting the complexity of solvers is something that I find to be very much black magic. So very often I see unintuitive results in the runtime. And this is also something that can be a bit better in dedicated tools, I would say, because there you have a bit more insight. This is also one difference between MILP and SAT. I would say that in SAT you have a bit less insight in the progress of the tool. So in MILP you can usually have some metrics like the remaining gap, which tells you a bit about the runtime and which can also help you evaluate whether one model is more efficient than the other without fully running it. Yeah.
Okay, thanks. And my second question is, so this is a funny question. So if I want to design a cipher and take a particular attack, and I want to misguide the guess and determine solver with my design. I mean, I want to design a cipher such a way that, for example, in differential attack, if I use a guess and determine solver to find a differential distinguisher, it will misguide the solver. So is it possible such a design, or is there any
What do
work?
you mean by misguide?
I mean, guess and determine solver work in a particular way.
Hmm.
If I understand the strategy and try to misguide it with my design, is there any?
The question is, what would your benefit be? Because essentially what it would mean is that the solver is slower than it would have to be, I guess. This is
Yes.
one of the potential
Yes.
consequences. Now, I don't know if this is a worthy
Yeah.
goal, even as a backdoor designer or something like that.
Okay.
I mean, there are some not misguiding, but actually very clever strategies that you can use to make your solver slower. One of the things to do is do a weakly aligned design instead of a strongly aligned one. It will be a lot more work for the solvers. They may fail to do anything, but you actually might also have improved your design because you may have increased the weight quite a bit without making it as easily measurable. So
Okay. Yeah, it was a funny question.
but a
Thank you.
serious answer. So
Are there any other questions?
Sorry. I'm not an expert on the design, but I see lots of development people that design the Cryptanalytics are based on the tools, these tools. And I'm curious about if there are the community about the SAT or MILP community are aware of our activity or not.
They are, I would say, at least to some extent. So in particular, the SAT community, they're usually very interested in finding good benchmarks for their solvers or finding way to improve their solvers. And cryptography is one of the areas where they've been looking at. However, they've mostly been limiting themselves to asking direct questions like a key recovery or a pre-image search problem instead of these characteristic search problems. But for example, I've recently been chatting quite a bit with a team in the University of Windsor. So some of the contributors of the STP project, and they are actually very interested in what they can do inside the SAT solver in order to make it more efficient. So they've had quite a lot of clever ideas how to improve a solver specifically for this SHA-2 characteristic search task. So there is some awareness, I would say. But I definitely think it would be good to talk more to each other, yes.
Thank you very much.
Some features
Any other? Yeah.
I should also maybe as a follow-up mention efforts to, for example, like the Crypto Mini-SAT solver, which tries to extend the basic CNF-based description language by things like an XOR model, because XORs as a CNF are horribly complex. And so by trying to include this alternative language in the solver or in a pre-processing step can also help quite a bit, and was also done specifically for cryptographic applications.
Thanks for the really nice overview of the topic. So my question is more about an opinion. So all these tools seems to somehow generalize the attacks that we know. Have you ever thought about like a tool that helps finding new attacks?
That's, of course, a difficult question, because how do you look for things that you don't know yet? I think this applies to manual cryptanalysis just like it does to tool-based cryptanalysis. I think one thing that tools can definitely help us in is explore the structure of a cipher and try to design or to learn more about its behavior based on the results that we can get easily from tools. And then by having a look at the structure, maybe we have some ideas or insight that that actually tells us something that we can use in an attack. I would say one other direction that tries to do this, so try to find a new kind of attack we don't know yet, is the area of neural cryptanalysis, where you try to throw some machine learning at the problem, try to teach it to distinguish things, and then have a look at what it actually distinguishes without telling it beforehand what it should be looking for. So I think this also goes in the direction of trying to find new attacks or new types of distinguishers instead of following the known structure of a distinguisher and looking for a particular instance of that.
So maybe as a follow-up question, so what about algebraic attacks? Do you think you can set up similar tool for algebraic attacks?
Well, there are actually tools for algebraic attacks, at least for certain algebraic attacks. One that I mentioned in the beginning was these monomial trails, which you can use to build integral attacks. And to find them or to prove the non-existence of monomial trails, you can also use a SAT-based or MILP-based model. So this is one direction. Of course, there is a whole other family of tools and solvers that I didn't talk about at all, like, for example, Gröbner bases, which also fall in the algebraic category, but which are so different from what I talked about that I didn't even mention them. I think one difference is that algebraic properties are often deterministic properties. So the search for them is in nature a bit different than the search for statistical distinguishers, I would say, because you don't really try to optimize any cost functions or probability or something like that. So this makes the problem a bit different. And this is maybe also the reason why integral attacks are by far underrepresented, for example, in the different frameworks, just because they are quite different from. So we do have the notion of characteristics there, but it's quite different than in the statistical settings. One thing I should also mention is, of course, when looking for integral distinguishers, we can't only do this. So we of course, we have different options. We can do this based on the degree or monomial or division trails or something like that. But we can also turn other attacks into integral attacks. So one example that I showed earlier was based on a zero correlation distinguisher that has been turned into an integral attack. So there we can use the existing tools and modeling strategies to first find the zero correlation distinguisher and then turn it into an integral distinguisher. So that's another way how to do it.
So we're out of time. Thanks a lot, Maria. So we can thank Maria again.